Swansea, and I'm going to talk about our work on no reference image quality assessment for images rendered by Monte Carlo rendering albums. So I'm interested in images that look like this. It's a little hard to see that one on the left, but these are images produced by Monte Carlo rendering albums, specifically path tracing, bidirectional path tracing. And they're computed by taking lots of ray samples coming out of a virtual camera. We intersect them with the scene geometry, with walls, with objects, and we bounce them around based on the probability with which light particles in real life would have actually scattered. One of the issues with these kind of rendering algorithms is that they take an awful lot of computation to give you good images. If we take just one ray sample out of the camera and bounce it around, whatever amount of energy we get back that went along that path, that's not representative of the color that pixel should really have. We need an equilibrium of lots of samples, lots of photons going through that same pixel, and we average them together to get a robust result. This means that early in the rendering process, when we haven't done much computation, we end up in a situation where pixels will look noisy, they'll look distorted compared to each other, and some pixels will look very bright and some pixels will look very dark. And it just comes down to the random chance with which paths get sampled. So in such cases, we care about evaluating the quality of these images. It's hard to see that in the outer focus regions up here in the full image, it's actually quite noisy. There's lots of speckles going on. And we care about whether or not these kind of distortions are perceivable, whether people can actually see them. Two images to one person might look very similar, and to a different person who's spent more time looking at different types of distortions, they might look very similar or very different comparatively. So we care about to what degree these distortions affect the images that we're looking at. So in full reference image quality assessment, in full reference image quality assessment, we would have access to both a ground truth image, a true image that we know is correct, it's been rendered to this high degree of computation, and it's very smooth in terms of its incidental structure. And then we have test images, which are rendered maybe by different kinds of rendering algorithms, different ones that we care about comparing to each other. And because it's got far less computation put into it, it's much noisier. And if we run a standard image quality assessment method, we can compare the two, and we might get a map like this that comes out and says what the distribution of error across this image is. Sometimes these methods are weighted by human perception, so they'll say, even though these two parts of the image are very different, they're different in a way that nobody would be able to notice because it's in a very dark region of the image. So it's harder to see the high frequency details. So that's all very good when we have both the reference image and the test image that we care about, but during the rendering process, unless we're actually testing different algorithms, but during the rendering process, we only have access to the image that we've produced so far. We don't know what it's meant to be at the end. If we did, then we wouldn't need to keep rendering it. We just call it a day. So we care about whether or not we can still evaluate this image and determine its quality across the at each spatial location without having access to that ground truth. And we can do this with no reference image quality methods by comparing our image to a learned distribution of what images should look like. So if we train a method based on lots and lots of converged images, which look correct, and then we show it one which doesn't, well, it should be able to pick out the small details here and tell us, okay, well, that doesn't look like what a true image, a correct image is supposed to look like. The vast majority of the work in this area in the past has been done using publicly available data sets. These data sets were constructed of natural images, photographs, and they've been taken and synthetically distorted. So in this case, it was some Gaussian sort of noise or some salt and pepper noise. We've got some color quantization, fast fading, and some block level artifacts where they've just taken whole blocks of the image and set them to a single color. And these are all well and good for testing certain things, and there's user studies that go along with these data sets, and they have a couple of 100 people, and they say which of these images looks better, or does this image look good, does this image look good? We get these mean opinion scores from user participants, and then we can try and train methods and say, okay, well, here's what our metric says, here's what the user said, let's try and train our metrics to be closer to what the user said for these. So we try to teach our methods about the perception of different distortions based on how we see users experiencing those distortions. But that requires that the kind of distortions in the dataset are representative of the kind of distortions that we actually see. when we look at these sort of images. And in general, for Monte Carlo images, these kind of distortions synthetically added to photographs aren't very accurate to what we actually see in our data. So we developed a new data set. We rendered these 5 different scenes to varying degrees of quality. We did it with 7 different Monte Carlo rendering albums. We had path tracing and bidirectional path tracing, metropolis light transport, and several other variations on advanced Monte Carlo rendering techniques. Each of these algorithms has different noise profiles or different types of distortions that appear throughout the rendering process. Some of them start very high quality and then very, very slowly converge towards the true solution, whereas others will start very noisy and quickly converge towards the true solution. So they go in different ways, and it's all based on the stochastic sampling techniques that they use. So we rendered these images out to all different degrees of quality. Here I have the ground truth image rendered to, I think, 500,000 samples per pixel, somewhere in that ballpark. And here is the same, that red crop window, at each sort of power of 2 samples that we added, so 2 samples, 4 samples, 8, and so forth, going all the way through. And you can see that, it's probably, I would say it's about here, it's about halfway through roughly, that the image becomes of sufficient quality that you can't really see the noise anymore. Or at least I can't. So this is what the problem is based on perception, and we spend so long looking at these images that we sort of become very sensitive to some kinds of distortion and blind to others because we spend so long looking at them. So your average user versus your expert user is going to have very different sort of perception on different kinds of distortion. So the goal is to be able to just look at the noisy image and give us a predicted map of where we think the error is going to be. And we're going to then hopefully be able to apply this to images that we haven't seen during training time. So in the case of our data set, we had 5 different scenes, and each time we've trained our model that we developed, we're going to leave one of these scenes out and train on the others. And you see they're all quite different in structure, so we hope that this shows that it is actually generalizing to content not found in the scenes it's been trained on. So the model we used is a fully convolutional neural network. The input size is some height by width by 3 channel RGB image, and the output is just going to be a single channel image of the same resolution, and we're just going to densely regress out a quality score for every pixel. So our model sort of goes in 2 phases. The image comes in, and we're going to use a series of 3 by 3 convolutions, widen our receptive field up to the point where the network can see about an 11 by 11 pixel window. And for each of these phases, it's seeing wider and wider. It's combining more of these locally extracted features. The reason why we use 5 of these layers to get to an 11 by 11 receptive field is because we're trying to mimic an existing full reference image quality assessment algorithm. We're trying to mimic the structural similarity index, and that uses an 11 by 11 local neighborhood to do its statistics over. So we widen our receptive field to that point, so we're seeing the same width of information, and then every layer afterwards is just going to be 1 by 1 convolutions. Essentially what this is doing is it's just taking whatever local features we've extracted from that neighborhood around each pixel and recombining them in some nonlinear pattern until we get sort of to the result we're looking for, the quality regression. So you can see for training, predicted structural similarity index is just based on the test image, whereas the reference is based off of the reference and the test image. So we want to minimize the difference here. For our loss function, regression-based problems, L2, L1 losses are common. We looked at a couple of different losses, and we benchmarked between them. I found that the Charbonnier loss, or pseudo-hover loss, which is shown here, is quite nice. And if we look at the plots, you can see the blue is an L2 loss, nice parabola, but the gradient keeps going up over time. And the further away you get from center, the green is the L1 loss, but that has this horrible discontinuity in the gradient at 0. And then we have the Charbonnier loss, which is sort of like the L1 loss, but it has a nice smooth transition at origin, and it just helps stabilize regression-based learning. For the full loss function, because we're doing an image quality assessment algorithm, and a common metric for sort of testing the performance of these methods is to look at correlation plots between the predicted and true quality values. So we've incorporated the Pearson's correlation coefficient into the loss function that we're using. So we jointly minimize the Charbonnier loss between the regression output, what we're expecting, but also we regularize it by saying that a distribution of things predicted at the same time should have similar correlation to the predicted values, should be highly correlated to them. And that sort of helps stabilize the training for a problem like this where we're doing quality prediction. We found that we needed to augment our data quite a bit in order to make this training stable. So these kind of models are very good at memorization if you give them the chance. And one of the big things that you have to do is you have to teach them about what's not important in the problem and stop them from focusing on that. If you have a biased sort of distribution of data that you've collected, then you need to remove all of those parts that it could pick up on that you don't want it to focus on. In our case, color was a big thing. We only had 5 different training scenes. There's a limited color palette of things that it could see. So one of the things we did was jitter or augment our data in the HSV color space so that it would begin to ignore color variations and would look at structure instead. So here are some test patches extracted from images. There's rotations, there's flips applied to them. And then each of these is multiple augmented variations on them with different flips, different rotations, and with the hue shifted around a color wheel in the HSV space. And we found that this was successful in stopping it from focusing on color information. It allowed it to generalize better to other scenes which had different color palettes. So here's a view of one of the training runs from one of the cross-validation runs. In this case, the Cornell box scene was left out. That's the scene with the red wall and the green wall and a couple of boxes in it. And we can see that while our validation loss did eventually plateau, it's still going down in terms of the correlation over batches of samples. So while the average loss is stabilizing, the actual correlation is still getting better, even in this case. Correlation between predicted and true values on a per pixel level are really consistent, and the little red cluster up here represents all the pixels within one of the test images. So just as a representative sign, an image which is very high quality will be robustly predicted across the whole image, and one that's low quality will also be robustly predicted across the whole image. It's not just picking up on, on average, okay, good quality predictions. So the results, we can get images like this. We have our Brown Truth Structural Similarity Index quality map and our predicted map. We can see that they're very similar. There's a couple of key differences, some areas in the really dark regions at the base of the cube, which are very hard to see down here. But in general, it's producing good enough results that these are actually usable. These are giving us enough information that we can go in and actually sort of improve our rendering process. So we compared to a variety of existing no reference quality metrics. Many of these weren't, all of these were not designed for Monte Carlo images. They were designed for the publicly available image data sets with the natural photographs synthetically distorted. And I think this is a big problem. Those data sets just aren't representative of the kinds of distortions that we're looking at when we look at Monte Carlo images. So we really need to have methods trained on domain data, domain distortions.
Thank you very much. We still have some time, so we can have more 2 or 3 questions. Okay, any questions? Okay, so I think one of the you also mentioned that one of the problems that you mentioned, okay, is that you only rendered 5 scenes so far.
Yes.
So from the scenes that I see, okay, they are mostly indoor. Have you considered other situations, say for some outdoor scene, refraction, something like this?
So some of the scenes do have refraction, they do have the caustic illumination in them. The reason we did mostly indoor scenes is because it limits the directions that light can come from, which makes specular highlights, the salt and pepper noise, more likely to be visible in the images. If you do an outdoor scene with a very wide area light over the top, then all of that diffuse illumination washes out the high frequency noise. You wouldn't be able to see that as clearly.
Any other questions? Yeah, I think that's good. Okay, thank you very much, Dan.